Welcome back. So good to have you again with us. We are going now to move on to a new part of the course. The slides are already on the Moodle. I give you, by the way, a bit of reading material. So there's always the textbook chapter. I might sometimes throw in one more mandatory reading material, but most of them is optional, right? So I also put them in there. Do not underestimate the optional part. Even if it's optional, reading them still, structures your thoughts in your brain along the everything going on in big data. So it's still a good idea to try to read them, even though it's less to know by heart than the mandatory parts. All right. So data models. What have we seen so far? We have this technology stack with all of these levels, and we've already built on some of the levels. For example, storage with S3, HDFS, Azure Blob Storage, cloud storage, Dynamo, head coding very briefly. We've looked at syntax, XML, JSON, bit of YAML, data models. We've seen now a bit with tables, with the return of the table for the big data with the white column stars, right? We even saw how we can have trillions of rows in there, and we are going to work our way up, right? Now I have to just click directly in here with my finger because the clicker had the wonderful idea of stopping working, but I should have one delivered by tomorrow. So then I will be able to click normally again. I would like to do a top 10 of what we have learned so far regarding big data, which are the high-level design principles of what we do at large scales. Principle number one is learn from the past. Never underestimate what our ancestors have already been doing, and in particular, the mistakes that they have made. In particular, do not underestimate relational databases and data independence. This is here to stay. All the relational algebra, selection, projection, this is still true. We have to redesign the whole thing on a cluster, but a lot of principles are still true. It's very important, and people do these mistakes all the time, right? What I told you, and I will also talk about that again, is a lot of people have a bias against the XML related ecosystem, probably because of its complexity and that it involves a lot of things. So it's tempting to say, XML is too complicated, let's go to JSON. It's so much simpler. The problem is that a lot of that has been done throwing away the whole XML lessons. Just we know better, let's do something simpler. We don't need schemas, we don't need query languages, we don't need navigation and so on. The problem is that after a couple of years, they did realize that they needed it after all. And it's sad because we actually lost a few years. If we had, from the very beginning, used the lessons coming from XML and then designed equivalent technologies for JSON based on the lessons learned from XML, simpler, of course, we would be years ahead in terms of the enterprise readiness of JSON. It's on the way. I think it will happen. There will be probably some convergence and some maturation of the whole JSON ecosystem. It's already in a pretty good state today, but it's just taking a bit more time than it should have. And so the lesson for later, if you design new systems, always take time to read through the literature, see what's already been done, see if you can learn a few lessons, because it will save you time to not repeat the mistakes that other people have been doing, right? And in fact, Richard Feynman has said several times that he wishes that in the academic community for publications, we wouldn't only publish and accept for publication successful papers that tell you what has worked, but it would be nice if we could also publish papers that explain what didn't work. And of course, it's hard to get that in because it's a negative result, right? We tried this and it didn't work. Who wants to read this? But the thing is, we should be reading this, and it would be really valuable to be able to know the things that didn't work, because this is as valuable to share as what worked. And when somebody gets a Nobel Prize, you see what was successful. You don't see the 999 other things that were not successful before succeeding. So this is very important. The second thing that we did in order to scale things up at larger scales is we simplified a lot of things, right? So For example, for storing on S3 or HDFS, well, even more so on S3 and Dynamo, we just stick to a key value model, flat. So we have keys and we associate them with values. But it's so simple that we can have billions of keys. That's the power of this simplicity. In a way, that's also the reason why things are moving in the direction of JSON, right? It's a bit of a simplification for a certain number of things, and we will see in this lecture that JSON is also kind of closer to relational tables in many respects, but we will see this. So we keep the design simple, and that is something that is extremely important to keep your sanity, you know, to be able to have it work in a way that you understand. All right. Number 3 is to modularize the architecture, which goes with keeping things simple, because it's so much easier to focus on a single layer of the architecture and do it well. And what you do when you focus on the layer of the architecture is that you assume that the rest is also already built, and you just use it, and then you expose something to the upper layers. So you are somewhere in here. And some people ask me, like, you know, what's the purpose of HBase? Why doesn't it have, you know, some high-level SQL and so on and so on? So why do we go on the halfway, exposing some get, put, delete, scan API while still exposing tables? Well, you really have to see HBase as a layer in here. It's not the final product, it's just a layer. It's a layer that builds on top of HDFS. HDFS provides you this way to scale with an insane number of bytes in the same file across thousands of machines, tens of thousands of machines. But it doesn't have random access. You can only write files, and that is very slow. What HBase gives you is the random access on top of that, plus some tabular structure. It kind of can be seen as some sort of way to index what is on HDFS, right? Thanks to table. It's a very abstract way of putting that. So basically, we have HDFS here, and we put HBase on top. But of course, HBase will expose its functionality to other systems. And there are, in fact, higher level systems on top of HBase, like Hive, that expose SQL. Then you can use SQL. It will flow all the way down to HBase and all the way down to HDFS. So you see, it's a complex stack that we are building. And depending on what you are doing, you put yourself on that or that level of the stack, and you build what you are building for this or that customer or this or that user. But what is very important is that as the semester elapses, these seemingly unrelated courses on different level of the stack, they in fact all fit together as in that same stack, interacting with each other. It's just that every week we go at some place in the stack and go through the details of that. But it's all connected. Then the next principle that is also related to simplifying things is that at very large scales, it's so much easier when things are a bit homogeneous. For example, you have trillions of rows, you have thousands of blocks, and so on. So when things look homogeneous on the very high level, it allows you to scale, because if it's homogeneous, you just spread it all over the cluster, and that's it, right? You just have blocks, you just spread them over the cluster. You have rows, you just partition in regions and spread them all over the cluster. So this is the idea. However, homogeneity at large scales goes hand in hand with heterogeneity at small scales. And this is because of data variety, that not everything is highly structured as in a relational database. The world is more diverse than that, and real world data might be more heterogeneous. We will see also as part of the data models how it's related to denormalized data. But we basically are designing systems that are small scales allow for some heterogeneity in the data, missing values, additional values, different types, and so on. While at the large scale, we have a model that allows us to spread it nicely all over the cluster, right? So this is heterogeneity in the small versus homogeneity in the large. Then, I can't say it often enough, data independence. We, at every layer of that technology stack, we nicely separate the layers. We have a logical layer and a physical layer. Of course, it depends on the layer you are in, right? So from the perspective of HBase, HDFS is a physical layer, right? and HDFS is a logical layer. But from the perspective of Hive, which exposes SQL, it's HBase that is the physical layer, and Hive provides the logical layer. But HDFS will disagree. HDFS thinks of itself that it is the logical layer, and the physical layer are the hard drives on the machines. So it's only a matter of perspective, right? You build the stack, but every time you have an API in the stack, you have the logical layer that is on top, the physical layer that is below, and the trick is to have such a clean and nice API that you isolate the other users from what's going on the other layers, right? There is a very nice expression that I think we got from the computer network people when we talk about the logical and physical layer of the APIs. It's like north and south, like you have the north side of the API that goes up and the southern side that goes down. It's a nice geographical way to look at the technology stack. All right, so yes, data independence. Very important, because otherwise you cannot keep your sanity, right? If you try to implement directly a SQL system that is ACID compliant directly on the machines on a cluster, you will have a very, very, very hard time. But if on the contrary, you first build HDFS and then HBase and then Hive and so on, layer by layer, this is much, much easier, and you can even decentralize by having several teams handling the components. Then, related to homogeneity in the large, we shard the data. It means we will partition the data. We have plenty of names for that: a shard, a chunk, a split, a block, partition, and so on, a region. So there are many ways, a tablet. But the idea is that we shard the data into partitions that helps spreading it all over the cluster, right? So this sharding, it's also useful for batch processing, because then we write all of that at the same time to HDFS in order to write an entire file. It's also a way to avoid the random access. So we shard the data. And what goes hand in hand with sharding the data is replicating the data, is that not only do we spread the partitions all over the cluster, we spread them multiple times. Every partition is going to go to 3 different places, for example, like an HDFS block goes to 3 places, and so on and so on. Now, of course, you don't overdo it, right? As I explained, since HDFS is already replicating the data, there is no need for HBase to do the same, right? HBase anyway is storing in HDFS, so you don't need to again have this replication. But at some point, you need to do the replication. That's number 8. Then we have number 9, which is buy tons of cheap hardware. That's the secret. Scaling out. It's less expensive than trying to buy a computer with enormous amounts of memory or an enormous amount of cores. It's just cheaper to buy plenty of machines that you pile up in racks in the data centers. All right? And number 10, batch process. So the idea of having plenty of machines is to parallelize. That solves the problem between the capacity, so the amount of data you have and the speed at which you can read it. If you parallelize, then you can read in parallel. Batch processing is for solving the mismatch between the throughput and the latency. Remember, we can read the data much faster than before, but the latency hasn't improved that much. So if we don't pay attention, we're going to be waiting the whole time. We keep waiting and waiting and waiting, and then we spend idle time. This is what would happen if we use the HDFS as random access. We would just keep waiting every time. But thanks to batch processing, which is this idea, or one aspect of batch processing of flushing and compacting, we only ever write down entire files. This is batch processing, and that avoids the latency, right? So it's really a latency avoidance mechanism, the batch processing. All right? Who understands the link? So that parallelization is the way to solve the capacity throughput mismatch, and that batch processing solves the throughput latency mismatch. Who understands that? Right, many of you already. So continue to think about that. This is one of the most fundamental things to understand in big data. All right, that was number 10. So we are here. So we took care of storage, encoding, syntax, data models. So we'll remain here for a while because I still want to talk to you about data models, but this time not just tables, not just things that fit in rows and columns, right? So this is the menu for today. And that goes back. Okay, this is moving forward. You remember maybe that 2 weeks ago, I've told you about syntax. What is syntax for? It's about storing in a textual format data that can be in the form of tables, as in here. That's the example of CSV that corresponds to a table. But we also saw that we can have XML and JSON like this. So the syntax can be XML or JSON, and the data shape would be a tree. I just haven't shown you yet this in action, but I gave you the intuition of that when I built the building blocks of XML and JSON recursively. And you probably by now associated the notion of recursion with the notion of tree, right? Whenever you have a recursion, you get some sort of arborescent structure. So in a way, what you're seeing here is also a kind of data independence, but about the data itself, not the computer code. Because the data is stored physically as text, a series of symbols in some file. But when we read the file and process it, we don't want to think of it as text. We want to think of it as some structured data, in that case, a table with rows and columns. In fact, what we have here, when you open a CSV file in a spreadsheet software, you have a data model, in that case, the relational data model. And I just want to do the same thing now with JSON and XML. So if you remember JSON, I'll start with JSON. We had these 6 building blocks, right? Strings, numbers, booleans, nulls, and objects and arrays, right? So the first 4 are atomic. It's the leaves of the tree, as we are going to see, right? Inside a string or a number or a boolean or a null, you don't have nested structures. But inside an object or an array, then you do have a recursion. Inside an object, you have more values. Inside an array, you have more values, right? An object is a map, and an array is a list, right? So this is where the recursion is, and this is why we are going to get trees out of this. So here's my question to you. First, if I show you this, who here sees a tree? A lot of you already. On Zoom too? Do we have people on Zoom who see a tree here? We have 54 people on Zoom. Wow. Okay, very good. So we have raised hands on Zoom as well. Who doesn't see a tree yet? And that's okay. Who doesn't see the tree yet? Right? It's totally fine. I'm here to teach you to see the tree. I want you, at the end of the week, to see the tree when you look at these documents. And if you do, then my goal will have been achieved. But even if you already see a tree, the lecture is anyway important to you because we are going to model that tree. Okay, let's build the tree then, because if I claim there is a tree in here, I can draw it too, right? So let's draw it. First, you probably noticed that on the high level, this is a JSON object, right? Because you have these curly braces here and there. So this is an object. How many keys does it have? 3 or 2? 2. Okay, on the high, it has 3 in total, yes. And on the higher level, it has 2, foo and bar, right? So I can see that the key foo is associated with true here, and the key bar is associated with some array, but you see the array goes like this, right? It starts here and it ends here. This is nicely indented because I'm a human being. It makes it so much easier if I indent in that way. Doesn't have to, just for us humans, right? So bar is associated with an array like this. And now, so true, I cannot go down, right? That's already atomic, but array, I can go down. How many members, how many elements, how many values do I have in here in the array? 2, which is an object, and null, right? So I put here my object and null. And I still, so here I'm done, right? It doesn't go deeper than null. But inside the object, I have how many keys? 1, exactly. That's the third one that you probably saw earlier recursively.
We have a question.
Yes?
I just wanted to ask for a clarification. The green ellipses are basically labels on the connections, right?
Yes.
Okay.
Yeah, exactly. That's exactly why I didn't draw them as rectangles, but as a special symbol. And I will come back to that because that's a difference with XML. Indeed, these green ellipses here are just labels on the edge, on the arrow, right? It's just a name that I give to the arrow. Like in graph theory, you can do that sort of things. The nodes are the rectangles. It's object, true, array, objects. These are my null and foo. These are my nodes in my graph, right? And then this edge here that goes from object to true is annotated with a label foo. It just means that there is a key foo that leads to true, all right? So very good question, very important to notice that. Who sees a tree now? Okay, more people, that's great. So now I want you to be able to draw a tree like that for any JSON document that I give you. Who is able to do that now? Okay. Anything, you should be able to draw the tree. Right, awesome, perfect. Yes? Yeah, almost, okay.
In the case of an array, should we also annotate the edges so that we keep the index? Because the order matters, right? In
Yep.
case of an array.
You're absolutely correct. So here, I didn't do it here. It's when you go in the details of the modeling that indeed you have two ways of doing that. Either you consider that there is an order in the edges, in which case that's kind of what I assumed here, in which case you don't need to index. But if the edges are not ordered, then you need indeed a position that says this is 1, this is 2, this is, and so on. So I could indeed have put in here a little 1 in some ellipse shape and a little 2 in some ellipse shape. Absolutely, yeah. And here I kind of assume an order, and then you might be wondering, okay, but yeah, in an object there is no order, right? So why do we assume an order here? And we will see when we go deeper into the document stores that there's the theory and the practice. In theory, there is no order in the keys of an object, right? There is no order at all. In practice, try and use a system dealing with JSON that keeps shuffling your keys in all your objects. You're going to lose your sanity. This is why, even though the order doesn't matter, most of the JSON database management systems will be nice to you and will kind of try to preserve the order. So they will just take it in the order in which you provide it to the system. They will try to preserve it. But it's only to be nice to you. You should not rely on that order. It's only to make your life easier and keep your sanity. All right? Don't take it for granted, because there can always be optimizations and the order might change if you spread it on multiple machines, for example. Right? Does that make sense? Did I answer your question? Yes? Yes. Awesome. So what do we have now? Well, I've just done the same thing as with CSV. I had CSV as the syntax, and I had my table as the visual model. And now I did the same. I have JSON as text. You see, it's just a bunch of characters. But now we drew like this a tree. I just took another example. Who agrees that this is the same? Right? Okay. Who would have been able to do it? Awesome. Perfect. So you can try on more examples, just write down or take JSON documents from the web, and you can try to draw the tree like that. All right. Now, guess what? We can do the same thing with XML. So I tried to, and we are going to do it together. It's slightly more complex, but you can do that too. Who now sees that an XML document is a tree with this visual help? Right? Who doesn't yet? Okay, we'll go a little bit through it and explain. The idea is that elements are nested inside elements. All right, so we'll go through XML then. First, before we go into details of how to build trees for XML, this is coming back to the question you asked, because you're absolutely correct that the labels for JSON are technically put on the edges of the graph. In XML, the labels are actually in the nodes. If I want to express this in a casual way, in XML, the nodes know how they are called, but in JSON, they don't, right? So if I take an example here, if I ask this object here, this purple object, what is your name? It doesn't know. It doesn't know because the name is right there above in an edge leading to it. So this object doesn't know its name, right? In fact, if we'll see when you query the data, you navigate to it, you lost the upper part in there. But in the case of XML, it's different. Here I use the ellipse, but these are the actual nodes here that I have. And the name of an element is part of the node. So if you asked element foo, what is your name, element foo? It will answer, oh, my name is element foo, right? So this is a difference between JSON and XML. The labels are on the nodes. The names are on the nodes. It's actually very important as a difference because that actually makes XML perfect for taxonomies. When you have taxonomies and you need to design things that have names, XML is perfect for that, right? Especially an example, I will come back to it with data cubes, that accountants, for example, with balance sheets and assets and so on, they love XML. Because with XML, you can actually design a whole taxonomy with all the positions, Konti, I think it's called in German, that you have in the balance sheet. So XML is really, really good for that. All right, so now I'm going to be drawing trees for XML, and the fancy way of doing that is we will introduce the XML information sets, right? But actually, it's only about drawing trees. So, yes?
Thank you. So the JSON structure made me thinking, for example, in Python, there is a specific key in modules that is called the name with double underscores, and that holds the name of the object, kinda. So it is possible to implement the same thing with JSONs as well, right?
You're absolutely correct. So technically, this is an opportunity for me to say that for the same data shape, you can have multiple models. And in fact, even for the same syntax, you can have multiple models, right? The model that I presented for JSON is a model that is kind of database friendly or database systems friendly in the sense that the intent is to then have a query language, right? But you can have other ways of modeling JSON. You can model it in other ways. And if you want, nobody would prevent you of creating a JSON data model where you store the label on the nodes. You could absolutely do that. And if I understand you, this is what Python does. It's totally fine, right? This is one way. And for XML2, the XML information set is one of the ways to model XML data, but there are others. There are other ways, right? So there is no absolute truth or absolute model. The most important is that if you deal with data, if you query data, and it doesn't matter if it's CSV, if it's XML, if it's JSON, if it's YAML, you have to be aware of your model. You have to know how your model is structured. You have to know what the properties of every node are, what is on the edges, what is on the nodes, what you manipulate in your query language. This is super important. Because when you do that, then you design a system that is consistent and that is data independent. If you don't do it, if you basically create a model that doesn't have information stored, but when you think about it, you use that information, you're breaking data independence. Because you have information you shouldn't have, because you don't have it through the model, you have it from the disk physically. So it's very important to keep that in mind, right? So if you intend, for example, to be using Python and you want to use this name underscore special field, you need to be very careful that you update your model to have the names in there. And that way you have it on the logical level and it's exposed. The alternative is to say, no, I have it on the edge, I don't have it on the nodes, but that forbids you from using this name underscore field, right? It's really a decision. It's a matter of decision, but you should try to get your model as clean and data independent as possible. Does it make sense?
Yeah, thank you.
Yeah, thank you. Okay, just checking the time. Yeah, so you have a bit of time. All right. So let's draw trees for XML then. So I'm going to take this document. That is an XML document. Who sees a tree? Like to ask that, right? Plenty. Who doesn't see a tree? Okay, we're going to be drawing a tree for that one. Okay. So there is a standard called the information set that is kind of a guide to drawing trees for XML. It's a W3C standard, just like HTML or XML. And the idea is that it has building blocks, but this time it's not syntax building blocks, it's logical building blocks. There's actually a lot of them, but I'm not going to annoy you with that. I'm just going to talk about 4 of them: document, element, attributes, and text. And the others, I won't even bother you with that. It's some of that is also a bit no longer in use. So I'll focus on these 4. What are these? These are the nodes of my tree, basically. I have document nodes, element nodes, attribute nodes, and text nodes or character nodes, depending. So every node when you specify a data model, so you say, okay, these are the nodes of my tree, and then you specify the properties of every node in the tree. So let's look at these properties. This here is the document node. The document node is the top level of my document. That's the root of the tree at the very top. The fancy name for document node is document information item. Information item is just a fancy name for node, right? So what are the properties? I don't include all of them, but one property is children. You want to know what the child nodes are for that node. Well, in that case, the children, it's just the element metadata, right? So you have this virtual document node, and below the document node, you have the metadata elements, that is the top level element, right? So I put the documents nodes in purple and the element nodes in blue for that, right? And I write the name of that because this element knows that it's called metadata. Doc is not really a name, it's just to say it's a document information item. The document information item also has a version. I told you it's 1.0 or 1.1. It's not very different from each other, but this is basically taken from here, if you have it there. All right, so that's my first node. It's the root of the tree. Then I have element information items, element nodes. What are the properties of an element node? Well, let's take metadata as an example. One of its properties is the name, right? I didn't put namespaces in there because I didn't want to confuse you more than necessary. So I just didn't take any namespace. So it means that in my QName, I don't have a prefix. I don't have a namespace. All I have is the local name, right? I just wanted to make things simpler. So since I only have the local names and no namespaces, the local name of the element node is metadata, right? Then it has children. You can see the children, right? This is what there is between the opening and closing element tag. And I see that I have title and I have publisher. So I list my children here. It's element nodes, title and publisher. Attributes, there's nothing, right? You see there is no attribute in there, so it's just empty. And the parent, because in XML you can go back to the parents, there is basically the document information item. Why? Because that's the top level element, right? So it's directly attached to the documents. All right, for whom does that make sense? That is one node that corresponds to metadata. Let's do title and publisher, right? There are also element nodes. Title, well, the local name is title. What are the children? Well, it's just text. So it's the text information item systems group. Attributes, there's two of them, language and year. You see, they are inside my title opening tag. So I have two of them, language and year. And the parent of title is metadata, right? It's inside the metadata tags, right? Title is inside metadata. Who agrees? All right, let me move on to the next one. Publisher, its name is publisher. Children, ETH Zurich, it's just text, but it could go recursively with more elements, of course. Attributes, none. Publisher, you see it's empty. And then metadata is the parents also. Then I have attribute nodes. So let's take language. That's an attribute. It has a local name year, a value 2022. I don't know why I had this 2019 that remained there. It's supposed to be 2022. And owner element, it's just a fancy name for parents in the case of an attribute, is title because the attribute is within the title. All right, so that's an attribute node, an attribute information item. The other attribute information item here is year. Is language. The local name is language. The normalized value is EN. Why normalized? Because typically when you have attributes, you might drop a few white spaces at the beginning and at the end. So it's just for convenience. So you normalize things a little bit. And then the owner element is also title because here is, you can see here inside title. It's harder to do if I look there. This here is inside the title elements. Then I have text nodes. Well, technically, if you look at the standard, it even does that character by character with a node for every character, but it's much easier to simplify and just merge them into a single node, at least for drawing. So text information item has these characters here, systems space group, and the owner element of the text is the title, right? Just because this systems group here is inside the title. And the other one here. Why did I do that? Because I want to draw a tree. So now all of these elements, I showed you one per slide, one node on every slide. Now I can draw them together. In order to get my edges, I looked at these children and parent or owner elements, right? So this is how I get my edges, and I get this beautiful tree. Who agrees that this corresponds to the XML? All right. Now, why are we doing this? Because if you want to query the data and work with this, the last thing you want to do is look at the text and try to work on the characters. This is the last thing you want to do. You're going to lose your sanity doing that. If you do this instead and draw a tree and obtain that tree, this actually is something that you have in your memory, in your machine. You parse the document, you parse it into a memory structure that is a tree. These are actual pointers in your RAM, in your working memory of your machine, and you have this in the memory. And then when you work on the data, we'll see in a few weeks, we'll have query languages, you actually work with this. This is what you work with. You don't work anymore with the syntax. You work with the data model. That is why data models are so important. Yes?
For the attributes, are they also pointed to, or are they just stored in a struct?
No, they are pointed to. At least in this data model, in the information set, there are nodes of their own. And when you have a query language that manipulates XML, it really distinguishes every attribute as a node of its own, right? Of course, you can have some optimizations in your memory. It might be that the way you store these pointers there, you can absolutely organize them in a map, right? It might be that inside this, that's basically, imagine you do it in Java, right? So this is a Java object, your node. Then you could absolutely have some map, like a tree map, for example. And in that map, you map language to this pointer and you map here to this pointer. You just make it faster. So you can absolutely do this, but it's a physical implementation. In the data model, what you have is really an edge and a node. Okay, thank you. Thank you. Another question over there.
How would this tree change if we have namespaces? Would just
So if you have,
the
yeah,
name change?
that's a very good question. So in that case, you have two more properties, the prefix and the namespace, in addition to the local name.
And so, for example, prefix would just be another children of title?
No, no, it's a property. Let me show you. So in that case, you would have the local name and the namespace and the prefix in there. But it's resolved, right? Because the machinery I showed you with XMLNS, right? But this is a physical detail, the fact that it's done that way. When you have resolved your prefixes and namespaces, every node will have a local name, a prefix, and a namespace. And you store them in there, right? Does that make sense? Yes, another question there.
But isn't the point of namespaces that we can store separately? We can store everything in one namespace and then store everything in another one?
Almost. Yes, but on the physical layer.
Mm-hmm.
In the sense that you can have schemas namespace by namespace. It's useful to keep things tidy in the sense that just like you have modules in Python, one for mathematics, one for drawing things and so on, you can have taxonomies in XML that nicely classify the names in namespaces. But in that case, the tree that we are drawing, its purpose is querying. So you could, and there exist models that have namespace nodes. So you would have a namespace node that corresponds to the XMLNS that has the bindings. But if you store the namespace nodes instead of putting the namespace and the prefix inside the elements, you basically need more CPU usage at runtime because then you need to resolve them again at runtime. So in a way, the fact that you remove the namespace nodes and instead store the properties for every element, you make it faster at runtime by doing that. So if I give you a tree where every node already has the namespace, the local name, and so on, and then you have a query that says, give me all of the nodes that are in that namespace, this is going to be much faster than it would be if you don't store these properties, but only store the namespace nodes. Mm-hmm. Does it make sense?
Mm-hmm.
Yeah. All right. And there exist systems with XML that have namespace nodes, but typically when you query the data, we will see in languages like XQuery or XPath, you don't have namespace nodes, but you really have these properties on every element. Okay? But you don't need to worry too much about XML because again, we are going to focus on JSON a bit more than XML. So I'll still show you a bit of XML, but that's just for the ecosystem. All right. Still have a few minutes. Okay, so congratulations. Now you can draw a tree for any XML document and for any JSON document, and you will even have exercises to do that, just to make sure. And again, why are we doing that? Because the first thing you do when you read an XML or a JSON document is you parse it and build a tree structure in memory, right? And when you're done, you go the other direction. It's called serialization. You serialize the tree that you have in memory back to a text file on HDFS or any file system. So remember that, parsing, serializing, parsing, serializing. But when you work with the data, you don't work with the original file, you work with the memory representation corresponding to the data model, a table, a tree, a graph, depending on your data. Which brings me to the next step, because drawing the tree is only the first part. It's the data modeling. It's like getting it into memory. Now that we got it into memory, we might want to do new things, such as imposing structures on the data. And the idea is that we have these two steps called well-formedness and validation. I was very careful 2 weeks ago of saying that a JSON document or an XML document is well-formed. And I didn't say valid, I said well-formed. I hope I didn't overlook any, but normally I should have said well-formed every time. The reason is that validation means something else, validity. And be careful, because a lot of people confuse the two. So a lot of people will say that a document is valid when they actually mean it's well-formed. Well-formed just means you can parse it and draw a tree. That's what well-formed means. Valid means not only can you draw a tree, but you have a million trees that look alike, because they all are valid against the same schema. That is the idea, right? So we have this pipeline. We take a text document, we try to parse it to a tree in memory, and then we try to validate it as an extra step. So it's really a two-step where it's not well-formed or it's well-formed, and you only ask if it's valid or not if it is well-formed. It doesn't make any sense to ask for the validity of a document that's not well-formed, because you were not able to interpret it as a tree in the first place. All right? Now, and I will finish on that slide for today. You have Oxygen that I encourage you to download. It has these two buttons, even though it changes in every version, but normally it's like in Matrix, right? The red or the blue button. So the red button gives you the validity. It's a yes, no. Either it says yes, it's valid, or it says no, there's this and that validation error. And the blue one gives you well-formedness. It will say yes, yes, it's well-formed, or no, sorry, it's not well-formed, and it will show you the error, right? All right, so I really encourage you, because it's great to work with what we are doing now with both XML and JSON. So checking that you actually followed here. Of course, I assume exactly. That's always what happens all the time. So let me scroll down. We are today, October 24th. There you go. So I would like to congratulate you, because the white column store lecture is the toughest of them all, and you've mastered it, right? So congratulations on that. It's really the most difficult of all lectures. There's so much material in there, so many pieces that get assembled together. So take the time, ask questions, also in the exercises, and the data models should be a bit easier. All right, but it's good because I still have more than 80%. I've seen worse. I've seen worse years. So thank you very much for your attention, and I'll see you tomorrow at 9 a.m.